Somewhere above your head, the atmosphere is quietly changing in ways most people never notice. Invisible gases are trapping heat. Tiny particles are reshaping clouds. Storms are growing stronger, and the balance that once kept Earth stable is shifting. This is not a distant future. It is already happening now. In the next moments, we will break down what is really happening inside Earth's atmosphere layer by layer, and why scientists say this change is unlike anything in human history. If you want to see more deep cinematic science documentaries like this, make sure to like the video and subscribe to the channel. It helps bring more stories like this to life. Now let's begin. Far above the weather of Earth, beyond clouds, storms, aircraft, and drifting ice crystals, the atmosphere becomes difficult to define. The uppermost edge slowly fades into the darkness of space without a clear border. Molecules spread farther apart until collisions become rare. Hydrogen and helium move through immense distances with little interference. Some particles drift away, entirely escaping the pull of gravity after long interactions with sunlight and magnetic energy. This outer region is known as the exosphere. It forms the thinnest extension of Earth's atmosphere, a boundary that is not fixed, but constantly changing in response to energy arriving from the sun and conditions rising upward from below. The exosphere begins several hundred kilometers above the surface and stretches outward for thousands of kilometers more. In this region, the atmosphere no longer behaves like the dense air closest to the ground. Molecules travel in long arcs. Some rise high above the planet before falling back again. Others continue outward into space. The density becomes so low that a single cubic centimeter may contain only a few particles. Even so, this faint region still matters to the structure of Earth. Satellites pass through its outer layers. Charged particles from the Sun interact with atoms here before continuing downward into lower regions. The exosphere also marks the place where Earth slowly loses part of its atmosphere over immense periods of time. For most of human history, this region remains completely invisible. No person standing on the ground can observe it directly with the naked eye. Only after the beginning of the space age do instruments begin to measure its shape and motion. Satellites detect changes in atmospheric drag. Ultraviolet telescopes observe faint glows caused by hydrogen atoms scattering sunlight. Over time, these measurements reveal that the outer atmosphere does not remain stable. It expands and contracts in response to solar activity. During periods of intense solar radiation, the atmosphere heats and swells outward. During quieter solar periods, it cools and shrinks. In recent decades, observations indicate that another long-term change is occurring. Measurements from satellites show that parts of the upper atmosphere are cooling and becoming less dense over time. This trend differs from the warming observed near Earth's surface. The reason lies in the way greenhouse gases behave at different heights. In the lower atmosphere, gases such as carbon dioxide trap outgoing heat and raise temperatures. In the upper atmosphere, the same gases can increase the release of heat into space. The result is gradual cooling in regions far above the weather systems below. This cooling effect changes the structure of the exosphere and the layers beneath it. As temperatures decline, the atmosphere contracts slightly inward. The density at high altitude becomes lower than earlier measurements predicted. Satellites experience less drag than expected. Pieces of inactive spacecraft and fragments of debris remain in orbit longer, because the thin atmosphere no longer slows them as efficiently. Researchers studying decades of orbital data identify these patterns with increasing confidence. Observations indicate that the upper atmosphere today behaves differently from the atmosphere measured during the earlier space missions. The changes remain subtle from a human perspective. No person standing at sea level can feel the contraction of the exosphere. The effect occurs far beyond ordinary experience. Yet instruments reveal that the atmosphere has entered conditions no previous human generation has measured directly. Since accurate monitoring of the upper atmosphere begins only during the 20th century, the present shift unfolds within the entire period of modern observation. Satellites launched decades apart move through slightly different conditions, even at the same altitude. Long-term records show measurable changes in atmospheric density across solar cycles. Solar activity still remains the dominant short-term influence in this outer region. The Sun constantly emits streams of charged particles known as the solar wind. During eruptions on the solar surface, bursts of energy travel outward through the solar system. When these disturbances reach Earth, the upper atmosphere absorbs part of the incoming energy. Heating increases rapidly. Atmospheric particles spread farther apart and move outward. Satellite drag temporarily rises. These cycles repeat across years and decades according to the changing magnetic activity of the Sun. At the same time, researchers separate these natural cycles from slower trends linked to human influence. Sophisticated climate models combine satellite measurements, chemistry, and solar observations. Many studies conclude that increasing greenhouse gases contribute to long-term cooling and contraction in the upper atmosphere. Observations from NASA and other scientific organizations support this general picture, although exact rates vary between models and measurement systems. Scientists continue refining estimates because the upper atmosphere remains difficult to monitor continuously across all altitudes and latitudes. The exosphere also responds to changes rising upward from lower layers. Powerful storms below can generate atmospheric waves that travel thousands of kilometers upward. These waves disturb the thin gases of the upper atmosphere. Even earthquakes and volcanic eruptions may produce ripples detectable at extreme altitude. Earth's atmosphere behaves not as isolated layers, but as one connected structure extending from the surface into space. Energy moves slowly upward through this entire system. Disturbances in one region can influence another far away. In darkness above Earth, the exosphere remains almost empty. The curve of the planet glows faint blue below. Thin traces of hydrogen stretch outward into the blackness. Satellites pass silently through drifting particles separated by enormous distances. The atmosphere at this height appears delicate and nearly absent, yet measurements reveal continual motion. The outer edge breathes inward and outward under solar pressure. Temperatures rise and fall. Particles escape into space. Human activity alters chemistry far below, and the effects slowly extend upward into regions once thought beyond ordinary planetary change. The atmosphere has always changed across geological time. Earth once possessed very different mixtures of gases. Ancient volcanic eruptions, evolving oceans, and living organisms reshaped the air repeatedly across billions of years. Yet the present transformation unfolds during an age of continuous observation. Instruments orbiting Earth record changes as they happen. Researchers compare decades of measurements with increasing precision. In the exosphere, these records show a planet whose highest atmospheric boundary no longer behaves exactly as it once did during the beginning of the space era. The change remains gradual and quiet, unfolding molecule by molecule at the edge of space itself. Below the fading edge of the exosphere, the atmosphere becomes slightly denser and more active. Here, solar radiation directly shapes the motion and temperature of the air. This region is known as the thermosphere. It extends through a vast layer of the upper atmosphere beginning several hundred kilometers above Earth and continuing downward toward the mesosphere below. In this region, sunlight carries enough energy to separate electrons from atoms and molecules, creating electrically charged particles. Temperatures rise sharply with altitude, although the meaning of temperature becomes unusual in such thin air. Individual particles move with enormous energy, yet the total amount of heat remains extremely low because so few particles exist. The thermosphere receives constant energy from the sun. Ultraviolet radiation and X-rays strike oxygen and nitrogen atoms, transferring energy into motion. During periods of strong solar activity, this heating intensifies dramatically. The atmosphere expands outward. Satellites in low orbit encounter increased drag as the upper atmosphere swells into higher altitudes. During quiet solar periods, the atmosphere cools and contracts. These cycles follow the changing magnetic behavior of the Sun across approximately 11-year intervals. Researchers have observed these patterns continuously since the beginning of the satellite age. Unlike the calm emptiness of the exosphere above the thermosphere, contains more structure and variability. Streams of charged particles move through Earth's magnetic field. Winds travel across immense distances. Temperature differences between daytime and nighttime regions generate circulation patterns that slowly transport energy around the planet. The atmosphere here responds rapidly to solar conditions. A single solar eruption can disturb the thermosphere within hours. Instruments aboard satellites measure these changes with increasing precision. Accelerometers detect subtle variations in atmospheric drag. Ultraviolet sensors measure the brightness of glowing oxygen atoms. Radar systems track changes in ionized layers that influence radio communication. Over decades, these observations reveal not only short-term solar cycles, but also long-term trends. The thermosphere today appears cooler and less dense than earlier generations of measurements indicate. The reason again involves greenhouse gases, especially carbon dioxide. Near Earth's surface, carbon dioxide traps outgoing infrared radiation and contributes to warming. In the thermosphere, the process works differently. Molecules of carbon dioxide absorb energy from collisions with surrounding particles and release that energy efficiently into space as infrared radiation. The result is enhanced cooling. As concentrations of carbon dioxide rise throughout the atmosphere, the thermosphere loses heat more effectively. This cooling produces measurable structural changes. The thermosphere contracts inwards slightly over time. Atmospheric density at many satellite altitudes decreases. Scientific studies comparing decades of satellite tracking data identify reductions in density beyond what solar cycles alone can explain. Observations from NASA missions and international research programs support the conclusion that human influence now extends into the upper atmosphere itself. The consequences remain largely invisible from the ground, yet the thermosphere performs important functions for modern civilization. Many satellites orbit within this region. Earth observation satellites monitor forests, oceans, storms, and ice. Navigation systems rely on carefully maintained orbital paths. Communication satellites pass through varying thermospheric conditions during their missions. Even small changes in atmospheric density affect orbital calculations over long periods. The changing thermosphere also alters the behavior of space debris. Fragments from inactive satellites and old rocket stages circle Earth at high speeds. Normally, atmospheric drag slowly lowers their orbits until they burn up in denser air below. As the thermosphere becomes less dense, this clearing process weakens. Debris remains in orbit longer, increasing the number of objects moving through crowded regions of near-Earth space. Scientists studying orbital safety increasingly consider long-term atmospheric contraction when modeling future conditions around Earth. At the same time, solar activity continues to dominate short-term behavior. During geomagnetic storms, huge amounts of energy enter the thermosphere. The atmosphere heats rapidly and expands outward by many kilometers. Satellite drag increases sharply. Some spacecraft require orbital adjustments to maintain position. communication systems experience temporary disruptions as charged layers of the atmosphere become disturbed. Observations from recent solar cycles show that the thermosphere remains highly dynamic even while long-term cooling trends continue underneath these short-term variations. The thermosphere also contains part of the ionosphere, a region filled with electrically charged particles. Solar radiation strips electrons from atoms, creating layers that reflect and bend radio waves. This process allows some radio signals to travel beyond the horizon by bouncing between the atmosphere and Earth's surface. Changes in solar activity alter the structure of these charged regions. During strong geomagnetic storms, navigation systems may lose accuracy. Radio communication can weaken or fail temporarily across certain frequencies. Scientific understanding of the thermosphere improves steadily, but uncertainties remain. The region is difficult to measure continuously because conditions vary rapidly across altitude, latitude, time of day, and solar activity. Satellite missions provide valuable information, yet long-term monitoring remains technically challenging. Researchers continue refining atmospheric models to better separate natural solar cycles from slower human-driven trends. Observations strongly support upper atmospheric cooling, though the exact future rate remains uncertain. Far above the clouds, the thermosphere glows faintly in darkness. Oxygen atoms emit dim green and red light after absorbing solar energy during the day. Most of this glow remains invisible to human eyes, but sensitive instruments detect it clearly from orbit. Satellites move silently through thin currents of heated gas. Charged particles spiral along magnetic fields. Waves generated by storms far below ripple upward through the atmosphere, disturbing the motion of air even at these extreme heights. The thermosphere reveals how deeply connected Earth systems have become. Human industry changes the chemistry of the lower atmosphere. Those chemical changes slowly alter the cooling balance of regions hundreds of kilometers above the planet. Solar storms continue shaping the upper atmosphere as they always have, yet long-term measurements now show additional patterns emerging beneath natural cycles. The atmosphere that surrounds Earth no longer behaves entirely within the range observed during the earliest decades of human spaceflight. Subtle shifts continue unfolding in silence above the world, carried by radiation chemistry and the gradual accumulation of change. Near the polar regions of Earth, invisible forces shape the upper atmosphere into moving curtains of light. Streams of charged particles arriving from the Sun encounter Earth's magnetic field and begin to spiral along immense magnetic pathways toward the north and south. As these particles descend into the upper atmosphere, they collide with oxygen and nitrogen atoms. Energy transfers through each collision. Atoms briefly enter excited states before releasing light. Green, red, violet, and pale blue glows appear across the night sky. These shifting displays are known as auroras. Auroras form mainly within the thermosphere and upper ionosphere, where solar particles meet atmospheric gases under the influence of Earth's magnetism. The process depends on the existence of the magnetosphere, the vast magnetic shield surrounding the planet. Earth's molten outer core generates this field through slow movements of conductive liquid metal deep below the surface. The magnetic field extends far into space and deflects much of the solar wind away from the atmosphere. Without this protection, the upper atmosphere would experience far greater erosion from charged solar particles over geological time. The Sun constantly releases streams of plasma into space. Plasma is matter in which electrons separate from atoms, creating charged particles that respond strongly to magnetic fields. Most of the time, this solar wind flows steadily across the solar system. At intervals, however, the Sun produces powerful eruptions known as coronal mass ejections. These events send immense clouds of charged material outward at millions of kilometers per hour. When such disturbances reach Earth, they compress and disturb the magnetosphere. During these geomagnetic storms, energy enters the upper atmosphere rapidly. Magnetic fields twist and reconnect far above Earth, accelerating particles downward into the polar regions. Auroras brighten and spread farther from the poles than usual. Regions that rarely experience such lights may briefly see them glowing near the horizon. Satellites detect surges of energetic particles moving through the thermosphere and ionosphere. Instruments measure rising temperatures and stronger atmospheric circulation at high altitudes. The atmosphere responds immediately to these bursts of solar energy. Heated gases expand outward, increasing atmospheric drag on satellites. Charged layers within the ionosphere become turbulent and uneven. Radio signals passing through these regions may weaken or shift unexpectedly. Navigation systems relying on satellite timing experience temporary errors because radio waves travel differently through disturbed ionized air. During the strongest geomagnetic storms, communication systems, power grids, and spacecraft operations can all experience disruptions. Scientific records show that geomagnetic storms have always occurred throughout Earth's history. Ice cores and tree rings preserve evidence of past solar activity. Observatories around the world have monitored magnetic disturbances for more than a century. Modern satellites now provide direct measurements of solar eruptions as they move through space toward Earth. Researchers understand the basic physical processes behind auroras and geomagnetic storms with considerable confidence. Yet predicting the exact intensity and effects of individual events remains difficult because the interactions between solar plasma and Earth's magnetic field are highly complex. In recent decades, scientists observe growing interest in how changing atmospheric conditions may influence the behavior of the upper atmosphere during solar storms. The thermosphere has become cooler and less dense overall, yet geomagnetic storms still inject large amounts of energy into the system. Researchers study how these long-term atmospheric changes affect satellite drag during solar events. Some evidence suggests that the atmosphere now responds differently than during earlier decades, though many details remain under investigation. Auroras themselves provide visible evidence that Earth's atmosphere is not isolated from space. The boundary between atmosphere and outer space remains active and dynamic. Energy from the Sun constantly interacts with Earth's magnetic shield and upper gases. During quiet periods, these interactions remain subtle. During powerful solar storms, the effects spread across enormous regions of the planet. At high latitudes, the auroral sky moves slowly across darkness like flowing fabric illuminated from within. Oxygen atoms produce green light at lower altitudes and deep red light higher above. Nitrogen creates violet and blue tones near the edges of active auroras. The exact colors depend on altitude, atmospheric density, and particle energy. Because the upper atmosphere remains extremely thin, collisions occur less frequently at higher altitudes, allowing some excited atoms to glow for longer periods before releasing energy. Below the visible lights, invisible currents flow through the ionosphere. These electrical currents generate magnetic disturbances measurable across Earth's surface. Sensitive instruments detect fluctuations in the magnetic field during auroral activity. Scientists use networks of ground stations and satellites to monitor these patterns continuously. Observations from NASA ESA and other scientific organizations help researchers understand how solar energy enters Earth's atmosphere and spreads through connected systems. The magnetic shield itself is not perfectly stable. Earth's magnetic poles drift gradually over time due to changing flows within the molten outer core. Geological evidence shows that the magnetic field has weakened and reversed many times across Earth's history. Present observations indicate that parts of the magnetic field have weakened slightly during recent centuries, especially over portions of the South Atlantic Ocean. Scientists continue studying whether these changes influence upper atmospheric processes in significant ways. Current evidence suggests that the magnetic field still provides strong protection overall, though regional variations affect satellite radiation exposure and particle motion. Far above Earth's surface, the atmosphere during a geomagnetic storm becomes filled with motion and energy. Charged particles descend along invisible magnetic paths. Heated gases expand outward. Waves travel through the ionosphere. Auroras shimmer across the polar sky while satellites move through regions of disturbed plasma. The atmosphere at these heights no longer appears calm or empty. It behaves as a responsive outer skin connecting Earth to the activity of the Sun. The upper atmosphere reveals a planet constantly exchanging energy with space. Solar storms remain natural events shaped by the long life of the Sun itself. Yet modern observations also show that the atmosphere receiving this energy has begun changing in measurable ways. Cooling contraction altered density, and shifting chemical balance now influence regions once thought distant from human activity. The auroral skies continue glowing above the poles as they have for countless generations, but the atmosphere surrounding those lights slowly enters conditions unlike those recorded during the beginning of the space age. Below the thermosphere, the atmosphere enters a region of increasing density and falling temperature. This layer is known as the mesosphere. It extends from roughly 50 kilometers above Earth's surface to the lower boundary of the thermosphere many kilometers higher. Within this region, temperatures decline steadily with altitude, until reaching some of the coldest natural conditions found anywhere in Earth's atmosphere. Near the upper boundary of the mesosphere, temperatures may fall below -90 degrees Celsius during certain seasons near the poles. The mesosphere remains difficult to study because it lies too high for aircraft and weather balloons, yet too low for most long-term satellite orbits. Scientists rely on sounding rockets, radar systems, ground-based lasers, and satellite observations to investigate this remote region. Compared with the lower atmosphere, direct measurements remain relatively limited. Even so, decades of observations reveal that the mesosphere is changing in subtle but measurable ways. Air in the mesosphere is extremely thin, though far denser than the thermosphere above. Meteoroids entering Earth's atmosphere encounter increasing friction here, and usually burn apart into glowing trails of light. Most shooting stars visible from the ground appear within this layer. Tiny particles from disintegrating meteoroids remain suspended afterward, contributing microscopic dust that influences chemical and cloud processes high above the surface. One of the most striking features of the mesosphere appears near the polar regions during summer. Extremely thin clouds form at extraordinary altitude, glowing faint blue after sunset, while the lower atmosphere below has already entered darkness. These are noctilucent clouds, also called night-shining clouds. They form when water vapor freezes around tiny particles of dust under intensely cold mesospheric conditions. Because they exist so high above Earth, sunlight still reaches them long after sunset from the perspective of observers below. For much of human history, noctilucent clouds remain either absent or extremely rare. Reliable observations begin during the late 19th century, shortly after the eruption of the volcano Krakatoa. Over the 20th and 21st centuries, reports of these clouds increase in frequency and geographic range. Scientists now study them carefully because they may reflect changing conditions in the upper atmosphere. Research indicates that increasing methane and carbon dioxide concentrations contribute to mesospheric cooling. Methane rising into the upper atmosphere eventually produces additional water vapor through chemical reactions. At the same time, carbon dioxide helps the mesosphere radiate heat into space more efficiently. Colder temperatures and slightly greater moisture create conditions favorable for noctilucent cloud formation. Observations suggest these clouds may now appear brighter, more extensive, and more frequent than in earlier periods of recorded history. The mesosphere therefore presents another example of a surprising atmospheric pattern. While the lower atmosphere warms overall portions of the upper atmosphere cool, these opposite temperature trends emerge from the different physical behavior of greenhouse gases at different altitudes. Near Earth's surface, greenhouse gases trap heat within denser air. In the mesosphere and thermosphere, they increase heat loss into space. Researchers continue studying the exact magnitude of mesospheric cooling. Because direct measurements remain sparse and technically challenging uncertainties still exist, different instruments sometimes produce slightly different estimates. Even so, long-term observations from satellites and ground stations broadly support the conclusion that the mesosphere has cooled during recent decades. Atmospheric waves constantly move through this region. Storm systems, mountain ranges, and strong weather far below generate disturbances that travel upward through the atmosphere. As these waves rise into thinner air, they grow larger and eventually break, transferring momentum and energy into the surrounding atmosphere. This process strongly influences mesospheric circulation. Winds at these altitudes may reverse direction seasonally and vary dramatically between hemispheres. The mesosphere also plays an important role in atmospheric chemistry. Ozone remains present here in smaller amounts than in the stratosphere below. Reactive oxygen and hydrogen compounds participate in complex cycles shaped by sunlight and temperature. During polar winters, unusual chemical reactions occur in darkness and extreme cold. Researchers monitor these processes because they help reveal how energy and gases move between atmospheric layers. At night, the mesosphere sometimes produces faint natural glows known as air glow. Chemical reactions involving oxygen, sodium, and hydroxyl molecules release small amounts of light invisible to most human eyes. Sensitive cameras aboard spacecraft detect moving wave patterns rippling across the atmosphere. These glowing structures reveal the constant motion of atmospheric waves generated thousands of kilometers away. Meteor trails also illuminate the mesosphere briefly. As small rocks from space enter the atmosphere at tremendous speed, collisions with atmospheric particles heat them intensely. Most meteoroids completely vaporize before reaching lower altitudes. The mesosphere therefore acts as a protective layer, destroying enormous amounts of incoming material before it can approach the surface. Tiny fragments left behind contribute metals such as iron and sodium to the upper atmosphere, where they influence cloud formation and chemical behavior. Far above the weather systems of Earth, yet below the intense ionization of the thermosphere, the mesosphere remains a transitional region shaped by both space and the lower atmosphere. Solar energy influences its chemistry. Weather systems below send waves upward into its thin air. Dust from space drifts through its freezing temperatures. Human-driven increases in greenhouse gases slowly alter its thermal balance. The changes unfolding in the mesosphere remain invisible to most people. No direct sensation reaches the surface when temperatures decline at 80 kilometers above Earth. Yet scientific instruments detect these shifts clearly enough to reveal long-term patterns. The atmosphere in this region no longer behaves exactly as it once did during earlier decades of observation. Cooling trends, expanding noctilucent clouds, and changing circulation patterns together suggest that even the coldest and most distant layers above the weather are responding to planetary change. High above the darkened surface, noctilucent clouds drift slowly across the edge of twilight. Ice crystals suspended in thin air catch sunlight from beyond the horizon. Below them, the atmosphere thickens toward the regions where ozone winds and stable air currents dominate the sky above Earth's weather systems. Below the freezing heights of the mesosphere, the atmosphere enters a more stable and layered region known as the stratosphere. Here, the steady decline in temperature with altitude reverses. Instead of becoming colder, higher up the air gradually warms. This unusual structure exists because ozone molecules absorb ultraviolet radiation from the sun and convert part of that energy into heat. The result is a calm atmospheric layer extending from roughly 10 to 50 kilometers above Earth's surface, positioned above nearly all clouds and weather systems. The stratosphere appears thin and dry compared with the turbulent troposphere below. Air moves slowly upward in tropical regions and gradually sinks near the poles through a circulation pattern called the Brewer-Dobson circulation. This slow movement transports ozone water vapor and other gases across great distances over months and years. Winds within the stratosphere often travel in broad horizontal bands. Because vertical mixing remains limited, gases released into the stratosphere can persist for long periods before breaking down chemically. Ozone forms naturally when ultraviolet radiation splits oxygen molecules apart. Individual oxygen atoms then combine with other oxygen molecules, creating ozone composed of 3 oxygen atoms. Although ozone represents only a tiny fraction of the atmosphere, its role is critical. By absorbing much of the sun's harmful ultraviolet radiation, the ozone layer protects living organisms at Earth's surface from dangerous levels of genetic damage. During the 20th century, scientists discover that certain manufactured chemicals known as chlorofluorocarbons damage stratospheric ozone. These compounds remain stable in the lower atmosphere for many years before drifting upward into the stratosphere. Their ultraviolet radiation breaks them apart, releasing chlorine atoms that destroy ozone through repeated chemical reactions. By the 1980s, researchers observed severe seasonal ozone depletion above Antarctica, a phenomenon widely known as the ozone hole. The discovery marks one of the clearest examples of human activity altering the chemistry of the global atmosphere. Satellite observations, high-altitude balloons, and ground measurements confirm that ozone losses extend beyond Antarctica into other regions of the planet, though less dramatically. Increased ultraviolet radiation reaches the surface beneath depleted ozone regions, affecting ecosystems and human health. In response, nations around the world adopt the Montreal Protocol, an international agreement limiting the production of ozone-depleting substances. Over time, concentrations of many harmful chemicals begin declining. Scientific assessments now indicate that portions of the ozone layer are slowly recovering. Although complete recovery will require many decades because these compounds persist in the atmosphere for long periods. At the same time, the stratosphere experiences another major transformation linked to greenhouse gases. As carbon dioxide concentrations increase throughout the atmosphere, the stratosphere cools overall. This cooling differs from the warming observed near Earth's surface. Increased greenhouse gases trap more heat within the lower atmosphere while allowing the stratosphere to lose energy more efficiently into space. Long-term observations from satellites and weather balloons confirm this cooling trend. The lower stratosphere has experienced measurable temperature declines during recent decades. Volcanic eruptions, solar cycles, and ozone recovery all influence short-term variations, yet the broader cooling pattern remains evident across multiple studies. Researchers regard stratospheric cooling as one of the strongest indicators that greenhouse gases are reshaping the atmosphere from top to bottom. Temperature changes in the stratosphere influence atmospheric circulation. The polar vortex, a large ring of strong winds surrounding the winter poles, depends partly on temperature differences between polar and lower latitude regions. Variations in stratospheric temperature can alter the strength and stability of this circulation. At times, disturbances known as sudden stratospheric warmings disrupt the polar vortex and affect weather patterns far below. During these events, temperatures in parts of the stratosphere may rise rapidly within days while winds weaken or reverse. Scientists continue investigating how climate change influences these stratospheric dynamics. Some observations suggest that warming near Earth's surface and cooling in the stratosphere may alter the frequency or intensity of certain circulation patterns. However, the atmosphere remains highly complex, and researchers continue studying how these connections operate across long timescales. Water vapor also plays an important role in the stratosphere despite its dryness. Most water remains trapped below in the troposphere because cold temperatures near the tropopause limit upward transport. Yet volcanic eruptions, methane oxidation, and powerful storms occasionally introduce additional moisture into the stratosphere. Water vapor influences temperature, cloud formation, and chemical reactions involving ozone. Volcanic eruptions can temporarily reshape the stratosphere on a global scale. Large eruptions inject sulfur-rich gases high above weather systems, where they form reflective aerosol particles. These particles scatter sunlight back into space and cool Earth's surface for several years. At the same time, they warm portions of the stratosphere by absorbing radiation. Historical eruptions such as Mount Pinatubo in the 1990s provide valuable evidence of how stratospheric aerosols influence climate and atmospheric chemistry. Aircraft flying near the lower stratosphere occasionally leave long-lasting condensation trails under suitable conditions. Researchers study whether increasing aviation traffic influences cloud formation and atmospheric heating in this region. Although the effect remains much smaller than greenhouse gas warming, it illustrates how human activity increasingly reaches even remote atmospheric layers, once isolated from direct influence. High above the clouds, the stratosphere remains calm compared with the weather below. Thin ozone absorbs invisible ultraviolet radiation. Winds circle the poles in darkness during winter. Fine particles from volcanoes drift across continents and oceans over many months. Temperatures slowly decline across much of the layer as greenhouse gases alter Earth's energy balance. The stratosphere records both vulnerability and resilience within the atmosphere. Human-produced chemicals damage the ozone layer on a planetary scale, yet international action slows and partly reverses the trend. At the same time, greenhouse gases continue reshaping temperatures and circulation throughout the layer. Observations gathered over decades reveal an atmosphere whose stable middle regions no longer remain unchanged. Cooling air, shifting winds, recovering ozone, and drifting aerosols together mark another stage in the evolving structure of Earth's atmosphere. Within the upper regions of the troposphere and lower stratosphere, narrow bands of fast-moving air circle the planet. These winds are known as jet streams. They form where strong temperature differences exist between cold and warm air masses. Earth's rotation bends these moving air currents into long flowing paths that travel mainly from west to east. Although invisible from the ground, jet streams shape weather systems across entire continents and oceans. Storm tracks, rainfall patterns, droughts, and seasonal temperature changes all respond to their movement. The strongest jet streams usually develop near the boundaries between polar and temperate air. During winter, when temperature contrasts grow larger, the polar jet stream becomes faster and more pronounced. Another major current, the subtropical jet stream, forms closer to the equator at higher altitude. Together, these powerful rivers of air help transport heat and moisture around the planet. Jet streams do not flow in perfectly straight lines. They bend into large waves known as Rossby waves, named after the scientist who first described them. These waves allow warm air to move poleward and cold air to move toward lower latitudes. Under stable conditions, the waves shift steadily eastward. Weather systems travel along these patterns with relatively predictable motion. In recent decades, researchers observe that some jet stream behaviors appear to be changing. One important factor involves the rapid warming of the Arctic. Temperatures in northern polar regions rise faster than the global average, a process called Arctic amplification. Sea ice declines, snow cover changes, and darker ocean surfaces absorb more solar energy. As the Arctic warms, the temperature contrast between polar and mid-latitude regions weakens. Because jet streams depend partly on these temperature differences, some scientists propose that Arctic amplification may influence jet stream strength and shape. Certain studies suggest that weaker temperature gradients can produce slower and more wavering jet streams. Under these conditions, large atmospheric waves may persist longer in one position. Weather systems then move more slowly across regions, increasing the duration of heat waves, cold spells, heavy rainfall or drought. Observations indicate that some recent extreme weather events coincide with unusually persistent jet stream patterns. Long-lasting heat domes, prolonged rainfall, and stationary storm systems have drawn scientific attention to the possibility that atmospheric circulation itself may be shifting. However, researchers continue debating the strength and consistency of these connections. The atmosphere contains many interacting influences, including ocean temperatures, tropical variability, volcanic activity, and natural climate cycles. While evidence supports certain changes in atmospheric circulation, the exact role of Arctic warming remains an active area of research. Jet streams also interact closely with the stratosphere above. Disturbances in the polar vortex can sometimes influence the position and strength of the jet stream below. During sudden stratospheric warming events, disruptions high in the atmosphere may alter winter weather patterns across North America, Europe, and Asia. These interactions reveal that Earth's atmospheric layers do not function independently. Energy and motion pass between them continuously. Aircraft traveling across continents often use jet streams to reduce travel time and fuel use. Flying within strong west-to-east currents allows aircraft to move more efficiently. Flying against them requires additional fuel and longer flight durations. Pilots and meteorologists monitor jet stream conditions constantly because their exact paths shift daily. The altitude of the jet stream region also changes gradually as the lower atmosphere warms. Observations indicate that the troposphere expands upward while the stratosphere contracts slightly due to cooling. As a result, some atmospheric boundaries rise over time. Researchers continue examining how these structural shifts influence global circulation patterns. Moisture transported by jet streams strongly affects precipitation. Atmospheric rivers, long narrow bands carrying enormous amounts of water vapor, often travel along jet stream paths. When these moisture-rich systems encounter mountains or colder air, intense rainfall or snowfall can occur. Certain regions depend on such systems for seasonal water supply, while others experience severe flooding during unusually strong events. Climate models generally project continued changes in large-scale atmospheric circulation as greenhouse gas concentrations rise. Many models indicate a gradual poleward shift of some jet stream patterns. Storm tracks may move toward higher latitudes in several regions. Dry subtropical zones could expand while rainfall patterns shift across agricultural areas. However, regional outcomes remain uncertain, because atmospheric circulation emerges from highly complex interactions involving land, oceans, ice, and atmospheric chemistry. The Southern Hemisphere provides another important example of jet stream change. Over Antarctica, the ozone hole influences atmospheric circulation by cooling the stratosphere and strengthening certain wind patterns. Observations show that this contributes to shifts in the Southern Hemisphere jet stream, affecting rainfall patterns in parts of Australia, South America, and Southern Africa. As ozone slowly recovers, scientists study whether these circulation patterns may gradually adjust again in future decades. High above the surface, jet streams move with tremendous speed through cold, thin air. Winds may exceed hundreds of kilometers per hour, yet their motion remains fluid and continuous rather than violent. Satellite images reveal long curving structures extending across oceans and continents. Storm systems spin and travel beneath these currents like leaves carried along a river. The changing behavior of jet streams matters because these winds connect distant regions of the planet. Conditions in the Arctic influence weather far to the south. Ocean temperatures shape atmospheric waves thousands of kilometers away. Heat added to the lower atmosphere alters circulation patterns reaching around the globe. Researchers examining decades of observations increasingly detect signs that the atmosphere's major wind systems are responding to a warming planet. The changes do not unfold evenly or predictably in every region. Some years resemble earlier patterns closely. Other years produce unusual persistence in weather systems that remain stalled over one place for long periods. Scientific understanding continues developing as observations accumulate and climate models improve. Yet the atmosphere now carries measurable signals that large-scale circulation patterns may be shifting alongside temperature chemistry and atmospheric structure itself. Above the clouds, the jet streams continue circling Earth in immense flowing arcs. They guide storms across oceans, transport moisture between continents, and shape the movement of seasons. Within these high winds, subtle changes slowly emerge, carried across the planet through currents that never truly rest. Below the high winds of the jet streams, the atmosphere enters its densest and most active region. This is the troposphere, the lowest layer of the Earth's atmosphere, and the place where nearly all weather occurs. Clouds form here, rain falls through it, winds move across oceans and continents within it. Human life remains entirely contained beneath its upper boundary. Compared with the vast emptiness of the upper atmosphere, the troposphere feels thick, heavy, and constantly in motion. The troposphere begins at Earth's surface and extends upward to an altitude that varies across the planet. Near the poles, it may reach only several kilometers above the ground, while near the equator it can extend far higher because warm air expands upward more strongly. The upper edge of the troposphere is known as the tropopause. Above this boundary, the stable stratosphere begins. Temperature in the troposphere usually decreases with altitude. Sunlight warms Earth's surface first, and the surface then transfers heat upward into the air. Warm air becomes less dense and rises while cooler air sinks. This continual vertical movement drives convection, the process responsible for cloud storms and atmospheric mixing. Moisture evaporates from oceans, lakes, forests, and soil, entering the troposphere as water vapor. Winds transport this moisture around the globe before it eventually condenses into clouds and precipitation. The troposphere contains most of the atmosphere's mass and nearly all of its water vapor. It also contains the greenhouse gases responsible for trapping heat near Earth's surface. Carbon dioxide, methane, nitrous oxide, and water vapor absorb infrared radiation emitted by the warmed surface. Without this natural greenhouse effect, Earth would remain far colder and largely uninhabitable. Yet increasing concentrations of greenhouse gases strengthen this effect and alter the energy balance of the entire planet. Measurements collected from weather balloons, aircraft satellites, and surface stations show that the troposphere has warmed significantly during recent decades. The warming does not occur evenly across all regions or seasons, but the long-term trend remains clear across multiple independent records. Oceans absorb much of the excess heat, yet the atmosphere itself also stores increasing energy. As the troposphere warms, its structure changes physically. Warmer air expands. Observations indicate that the tropopause rises gradually over time, especially in tropical regions. This means the troposphere itself becomes deeper, while the stratosphere above contracts slightly due to cooling. Scientists regard this expansion of the troposphere as another measurable sign that greenhouse gases are reshaping the atmosphere on a global scale. A warmer troposphere can also hold more water vapor. The relationship follows well-understood physical principles. For every increase in temperature, air gains the capacity to retain additional moisture before condensation occurs. Since water vapor itself is a greenhouse gas, this creates an amplifying feedback. Rising temperatures allow more water vapor to enter the atmosphere, which then traps additional heat. This added moisture changes weather behavior. Heavy rainfall events become more intense in many regions because storms can draw upon larger amounts of atmospheric water. Observations across numerous continents show increasing frequency of extreme precipitation events, although regional patterns vary. Some areas experience stronger storms and flooding, while others become drier due to shifting circulation and evaporation patterns. The warming troposphere also influences atmospheric instability. Heat near the surface strengthens upward convection under suitable conditions. Thunderstorms may develop with greater energy when warm, moist air rises rapidly into cooler regions above. Tropical cyclones draw power from warm ocean surfaces and moist atmospheric conditions. While the total number of storms does not necessarily increase everywhere, observations indicate that the most intense storms are becoming more powerful in several ocean basins. Heat waves become more frequent and prolonged as average temperatures rise. During persistent high-pressure systems, warm air remains trapped near the surface for extended periods. Dry soil conditions can intensify the heat further because less energy goes into evaporation and more goes directly into warming the air. Cities often experience especially high temperatures because buildings, roads, and concrete absorb and release heat efficiently. At the same time, cold weather still occurs. Winter storms and outbreaks of freezing air remain part of natural atmospheric variability. Yet the overall balance shifts toward warmer conditions over long timescales. Climate records compiled from many regions show that unusually warm years now occur more frequently than in earlier periods of modern observation. The troposphere also carries enormous quantities of airborne particles. Dust rises from deserts. Sea salt enters the air from breaking waves. Smoke from wildfires drifts across continents. Industrial pollution releases sulfate, soot, and other aerosols into the atmosphere. These particles interact with sunlight and clouds in complex ways. Some reflect sunlight and cool the surface locally, while others absorb heat. Researchers continue studying how these competing effects influence regional and global climate patterns. Weather systems within the troposphere remain deeply connected to the oceans below. Warm sea surfaces release heat and moisture into the atmosphere, driving circulation patterns across the globe. El Niño and La Niña events in the Pacific Ocean alter rainfall and temperature patterns across many continents. Seasonal monsoons depend on contrasts between land and ocean heating. The troposphere therefore acts as part of a larger climate system, linking air, water, ice, and land together. From the ground, the troposphere appears familiar because all ordinary weather unfolds within it. Clouds drift across the sky. Rain darkens the soil. Winds move through forests and cities. Yet measurements reveal that this familiar layer is steadily accumulating heat and moisture. The atmosphere observed today differs measurably from the atmosphere recorded by earlier generations of meteorologists. The changes unfold gradually yet continuously. The tropopause rises. Warm nights become more common. Heavy rainfall intensifies in many regions. Heat waves persist longer. Atmospheric moisture increases. Scientific records from around the world show that the lower atmosphere has entered conditions unlike those measured during the early 20th century. The troposphere, once understood mainly as the region of daily weather, now also carries the long-term signal of a warming planet. Where the atmosphere meets the oceans, enormous exchanges of heat, moisture, and gas occur continuously. The sea surface forms one of the most active boundaries on Earth. Sunlight warms the upper layers of water during the day. Winds stir the surface into waves and currents. Water evaporates into the atmosphere molecule by molecule, carrying heat upward into the troposphere. In return, the atmosphere transfers momentum, rainfall, and changing temperatures back into the ocean. Together, the oceans and atmosphere operate as a single connected system regulating climate across the planet. The oceans cover more than 2/3 of Earth's surface and absorb most of the excess heat trapped by greenhouse gases. Water possesses a very high heat capacity, meaning it can store large amounts of energy while warming relatively slowly. Because of this property, the oceans moderate atmospheric temperatures and reduce sudden extremes between day and night or between seasons. Yet as greenhouse gas concentrations rise, the oceans steadily accumulate more heat. Measurements from ships, buoys, satellites, and deep ocean instruments show that ocean temperatures have increased significantly during recent decades. The warming appears strongest near the surface, but also extends into deeper layers. Scientific observations indicate that the oceans now store far more heat than during the early period of modern climate measurement. This warming alters atmospheric behavior because warmer oceans transfer additional energy and moisture into the air above. Evaporation intensifies over warmer water. Individual water molecules at the surface gain enough energy to escape into the atmosphere as vapor. This process removes heat from the ocean and transports it upward into the troposphere. When the water vapor later condenses into clouds and rain, latent heat is released back into the atmosphere, powering convection and storm development. Warm oceans therefore act as fuel for many atmospheric systems. Tropical regions illustrate this connection clearly. Strong sunlight heats equatorial oceans throughout the year, creating large zones of evaporation and rising moist air. This upward motion drives atmospheric circulation patterns that influence weather around the globe. Trade winds, monsoons, and tropical storms all depend partly on the transfer of heat and moisture from ocean surfaces into the atmosphere. As ocean temperatures rise, the atmosphere gains access to increasing amounts of moisture. Observations confirm that atmospheric water vapor has increased overall in response to warming seas and air temperatures. This added moisture influences cloud formation, rainfall intensity, and storm behavior. In many regions, heavy precipitation events become more severe because storms can release larger quantities of water over shorter periods. Tropical cyclones provide one of the clearest examples of atmospheric response to warm oceans. Hurricanes, typhoons, and cyclones form above sufficiently warm sea surfaces where moist air rises rapidly and begins rotating around low-pressure centers. As water vapor condenses within these storms, large amounts of latent heat strengthen circulation further. Scientific studies indicate that while the total number of tropical cyclones may not increase consistently worldwide, the strongest storms are likely becoming more intense as oceans warm. Marine heat waves also become more common. These events occur when ocean regions remain unusually warm for extended periods. Persistent atmospheric patterns, weak winds, and long-term climate warming can all contribute. Marine heat waves affect atmospheric circulation above them, while also damaging marine ecosystems below. Coral bleaching, shifts in fish populations, and declining oxygen levels often accompany prolonged ocean warming. The oceans also exchange gases continuously with the atmosphere. Carbon dioxide moves between air and seawater according to temperature, circulation, and chemical balance. Cold water absorbs carbon dioxide more readily than warm water. For decades, the oceans have absorbed a substantial fraction of human-produced carbon dioxide emissions, slowing the rate of atmospheric accumulation. However, this process changes ocean chemistry by increasing acidity. As carbon dioxide dissolves in seawater, it forms carbonic acid. Ocean acidity therefore rises gradually as atmospheric carbon dioxide increases. This chemical shift affects marine organisms that build shells or skeletons from calcium carbonate. Although the changes unfold slowly from a human perspective, they represent major alterations in ocean chemistry. Compared with conditions before industrialization, ocean currents distribute heat around the planet. Warm surface currents carry tropical heat toward higher latitudes, while colder deep currents return water toward equatorial regions. One important system, often called the Atlantic Meridional Overturning Circulation, transports warm water northward through the Atlantic Ocean. Researchers study whether climate change could weaken parts of this circulation due to melting ice and increasing freshwater input into northern oceans. Observations suggest some long-term weakening may already be occurring, though considerable uncertainty remains regarding future changes. The atmosphere responds strongly to ocean temperature patterns. El Niño events develop when warm water spreads across the central and eastern tropical Pacific Ocean. These events alter rainfall, storms, droughts, and temperature patterns worldwide. La Niña events produce roughly opposite conditions. Together, these natural cycles demonstrate how closely atmospheric behavior depends on ocean conditions. Sea ice also influences the exchange between ocean and atmosphere. Ice reflects much of the sun's energy back into space, while dark, open water absorbs more heat. As Arctic sea ice declines, larger areas of ocean remain exposed during summer and autumn. Additional heat enters the atmosphere from these open waters, especially during colder seasons. This process contributes to rapid Arctic warming and influences atmospheric circulation beyond the polar regions. Above the oceans, the atmosphere carries immense streams of moisture invisible to human eyes. Clouds form where warm, humid air rises and cools. Storms gather energy from heated seas. Winds transport evaporated water across continents before returning it to Earth as rain or snow. The ocean surface continually breathes moisture and heat upward into the sky. Scientific measurements gathered across decades reveal that these exchanges are intensifying. Warmer oceans release more energy into the atmosphere. Marine heat waves become more frequent. Atmospheric moisture increases. Powerful storms draw upon expanding reservoirs of oceanic heat. The atmosphere above the seas no longer reflects the same thermal conditions measured during earlier generations of climate observation. The oceans once buffered much of the atmospheric change unfolding across Earth. They continue absorbing enormous quantities of heat and carbon dioxide even now. Yet this buffering alters the oceans themselves and feeds new energy back into the atmosphere above. Along the shifting boundary between sea and sky, the climate system grows warmer, wetter, and increasingly energized. Within the lower atmosphere, invisible gases determine how heat moves between Earth and space. Most of the atmosphere consists of nitrogen and oxygen gases that interact only weakly with infrared radiation. Mixed among them, however, are smaller amounts of greenhouse gases capable of absorbing and re-emitting heat. These trace gases regulate Earth's temperature through the greenhouse effect, a natural process that keeps the planet warm enough to sustain liquid water and life. Sunlight passes through the atmosphere and warms Earth's surface. The surface then emits energy outward as infrared radiation. Greenhouse gases absorb portions of this outgoing heat and re-radiate it in multiple directions, including back toward the surface. This slows the escape of heat into space and raises temperatures within the lower atmosphere. Without this process, average global temperatures would remain far below freezing. Carbon dioxide is one of the most important greenhouse gases because of both its abundance and long lifetime in the atmosphere. Before large-scale industrialization, atmospheric carbon dioxide levels remain relatively stable for thousands of years. Ice core records from Antarctica preserve ancient air bubbles showing that concentrations fluctuate naturally through glacial and interglacial periods, but stay within a limited range compared with present conditions. During the 19th and 20th centuries, human activity begins releasing large amounts of carbon dioxide through the burning of coal oil and natural gas. Deforestation also contributes by reducing the number of trees capable of absorbing carbon dioxide through photosynthesis. Cement production and industrial processes add further emissions. Measurements now show that atmospheric carbon dioxide concentrations have risen to levels not observed for millions of years according to geological evidence. Scientists monitor atmospheric carbon dioxide continuously at observatories around the world. One of the longest records comes from the Mauna Loa Observatory in Hawaii, where precise measurements begin during the late 1950s. The record reveals a steady upward trend with seasonal oscillations caused largely by plant growth and decay in the northern hemisphere. The increase continues decade after decade. Methane represents another powerful greenhouse gas. Although present in much smaller concentrations than carbon dioxide, methane traps far more heat molecule for molecule over shorter timescales. Methane enters the atmosphere from natural wetlands, agriculture, fossil fuel extraction, landfills, and thawing permafrost. Livestock, such as cattle, release methane during digestion, while leaks from natural gas infrastructure also contribute significantly. Atmospheric methane concentrations rise sharply during the industrial era. After a period of slower growth in the late 20th century, observations show renewed acceleration during recent decades. Researchers continue studying the exact contributions from agriculture, fossil fuels, tropical wetlands, and other sources. Methane eventually breaks down in the atmosphere through reactions involving hydroxyl radicals, yet its warming influence remains substantial during its lifetime. Nitrous oxide also contributes to greenhouse warming. This gas arises from agricultural fertilizers, industrial activity, and natural soil processes. Nitrous oxide persists in the atmosphere for long periods and also affects stratospheric ozone chemistry. Though less discussed publicly than carbon dioxide or methane, it represents an important part of the changing atmospheric balance. Water vapor remains the most abundant greenhouse gas overall, but its concentration depends strongly on temperature. As the atmosphere warms due to rising carbon dioxide and methane evaporation increases, and the air holds more moisture, this additional water vapor amplifies warming further. Scientists describe this process as a feedback rather than an initial forcing, because water vapor responds to temperature changes rather than driving them independently over long timescales. The warming influence of greenhouse gases can be measured directly. Satellites detect changes in infrared radiation escaping Earth. Surface instruments observe increasing downward infrared radiation reaching the ground. Climate models based on established physical laws reproduce observed warming patterns when greenhouse gas increases are included. Without these gases, modern warming trends cannot be explained adequately by solar variability or volcanic activity alone according to current scientific understanding. The atmosphere also contains aerosols that partially offset some warming. Sulfate particles from industrial pollution reflect sunlight and cool certain regions temporarily. However, these particles remain in the atmosphere for much shorter periods than greenhouse gases and carry harmful effects on human health and ecosystems. As air pollution regulations reduce sulfate emissions in some regions, underlying greenhouse warming can become even more apparent. Carbon dioxide does not distribute evenly at every moment, yet atmospheric circulation gradually mixes it around the planet. Winds transport gases between continents, oceans, forests, and cities. Seasonal plant growth temporarily removes carbon dioxide from the atmosphere, especially during spring and summer in northern regions. Fires, droughts, and decomposition later release part of that carbon back into the air. The atmosphere therefore functions as part of a larger carbon cycle, linking air oceans, vegetation, soils, and rocks. Over geological timescales, volcanic eruptions, weathering of rocks, and burial of organic material naturally regulate atmospheric carbon dioxide. Human industry now transfers carbon from fossil reservoirs into the atmosphere far more rapidly than most natural processes can remove it. Scientific evidence for the warming effect of greenhouse gases rests upon many independent observations. Thermometers show rising temperatures. Oceans accumulate heat. Ice melts across glaciers and polar regions. Spring arrives earlier in many ecosystems. Species shift their geographic ranges. The atmosphere itself stores more moisture and energy. Together, these observations align with the expected consequences of increasing greenhouse gases. Uncertainty remains regarding the exact pace and regional details of future climate change. Clouds, ocean circulation, ice sheet behavior, and ecosystem responses all introduce complexity into climate projections. Yet the fundamental physical relationship between greenhouse gases and atmospheric warming is among the most thoroughly studied principles in climate science. Above Earth's surface, molecules invisible to human eyes continually absorb and release infrared radiation. Carbon dioxide drifts through forests, cities, deserts, and oceans alike. Methane rises from wetlands and industrial infrastructure. Water vapor gathers over warming seas. The atmosphere slowly changes composition year after year. The transformation unfolds quietly because greenhouse gases remain colorless and diffuse. No boundary marks the transition from earlier atmospheric conditions to present ones. Yet precise measurements reveal a clear trend. The lower atmosphere now contains concentrations of heat-trapping gases far beyond those measured before industrialization. These molecules alter the movement of energy through the atmosphere itself, strengthening the greenhouse effect that shapes Earth's climate. Within the air surrounding the planet, chemistry and radiation now interact differently than they once did. The atmosphere still performs its ancient role of regulating planetary temperature, but the balance shifts steadily as greenhouse gases accumulate across the sky. Suspended within the atmosphere are countless tiny particles collectively known as aerosols. Some originate from natural sources such as deserts, oceans, volcanoes, forests, and wildfires. Others arise from human activity through industry, transportation, agriculture, and the burning of fossil fuels. These particles vary enormously in size, shape, color, and chemical composition. Though often microscopic, aerosols strongly influence how sunlight, heat clouds, and rainfall move through the atmosphere. Dust lifted from dry landscapes represents one of the largest natural aerosol sources on Earth. Powerful winds sweep across deserts and carry fine mineral particles high into the atmosphere. The Sahara Desert alone supplies vast quantities of dust that drift across the Atlantic Ocean toward the Americas. Satellite observations reveal enormous pale clouds stretching thousands of kilometers above the ocean surface. These dust plumes transport iron, phosphorus, and other nutrients that eventually settle into forests and marine ecosystems far from their source. Sea spray forms another major source of aerosols. Breaking waves eject tiny droplets of salty water into the air. After evaporation, salt particles remain suspended within the atmosphere. These particles interact with moisture and help form cloud droplets over the oceans. Biological activity within seawater can also release sulfur compounds that contribute to aerosol formation. Volcanic eruptions inject aerosols into the atmosphere with dramatic speed. Large eruptions release sulfur dioxide gas high into the stratosphere, where chemical reactions convert it into sulfate particles. These reflective aerosols scatter incoming sunlight back into space and can cool Earth's surface temporarily. Historical eruptions provide clear evidence of this effect. After major eruptions, global temperatures sometimes decline slightly for several years before the particles gradually settle out of the atmosphere. Wildfires generate another important category of aerosols. Smoke contains soot, organic compounds, ash, and other particles produced by incomplete combustion. In recent decades, some wildfire seasons grow larger and more intense, as drought heat and changing land conditions increase fire risk in various regions. Massive smoke plumes now travel across continents and oceans, darkening skies far from the original fires. Human industry produces additional aerosols through factories, power plants, shipping, and vehicle emissions. Sulfates form from sulfur-containing fuels. Black carbon, often called soot, arises from incomplete burning of coal, diesel, fuel wood, and biomass. Industrial processes release nitrates, metals, and organic particles into the atmosphere. Urban regions therefore contain complex mixtures of aerosols shaped by transportation, manufacturing, heating, and local weather conditions. Unlike greenhouse gases, aerosols usually remain in the atmosphere only for days or weeks before settling out or washing away in precipitation. Yet during their relatively short lifetimes, they exert powerful effects on climate and weather. Some aerosols reflect sunlight and cool the surface beneath them. Sulfate particles are especially effective at scattering solar radiation. Other aerosols absorb sunlight and warm the surrounding atmosphere. Black carbon strongly absorbs energy and contributes to atmospheric heating. The balance between cooling and warming effects depends on aerosol type, altitude, surface brightness, and cloud interactions. Because aerosol behavior varies greatly across regions and timescales, scientists continue refining estimates of their overall climate influence. Compared with greenhouse gases, aerosol impacts remain more uncertain, though their importance is widely recognized. Aerosols also influence cloud formation directly. Water vapor condenses more easily around tiny particles suspended in the atmosphere. Aerosols therefore act as cloud condensation nuclei surfaces upon which cloud droplets form. Changes in aerosol concentration can alter cloud brightness, droplet size, cloud lifetime, and precipitation patterns. Clouds forming in polluted air often contain many smaller droplets rather than fewer large ones. Such clouds may appear brighter and reflect more sunlight back into space. At the same time, smaller droplets collide less efficiently, potentially delaying rainfall. These complex interactions between aerosols and clouds represent one of the most challenging areas of climate science, because the processes occur across extremely small scales while influencing global atmospheric behavior. Black carbon produces especially important effects when deposited on snow and ice. Dark particles reduce the reflectivity of frozen surfaces, allowing them to absorb more solar energy and melt faster. This process contributes to warming in Arctic and mountainous regions. Soot from industry, transportation, and wildfires therefore influences both atmospheric heating and surface ice loss. Air pollution also affects human health directly. Fine particles small enough to enter deep into the lungs contribute to respiratory disease, cardiovascular illness, and premature death. Large cities often experience dangerous air quality during periods of stagnant weather when pollutants accumulate near the surface. Wildfire smoke can spread harmful particles across entire regions for weeks at a time. In many industrialized countries, air quality regulations reduced sulfur pollution significantly during recent decades. Cleaner fuels and emission controls lower concentrations of certain reflective aerosols. While this improves public health, it also reduces some of the temporary cooling previously masking portions of greenhouse warming. As sulfate pollution declines, underlying warming trends can become more pronounced. Satellite instruments now monitor aerosols globally. Scientists track dust storms crossing oceans, smoke spreading from wildfires, and pollution accumulating above cities. Aircraft and ground stations measure particle composition and concentration. These observations reveal an atmosphere filled constantly with moving material suspended between Earth and space. The atmosphere never remains perfectly clear. Fine particles drift through sunlight, shaping the colors of sunsets and the brightness of clouds. Dust from deserts settles into distant forests. Smoke from fires circles the planet. Industrial pollution rises above expanding cities. Volcanic aerosols spread silently through the stratosphere after eruptions. Scientific records show that the distribution and composition of atmospheric aerosols are changing alongside temperature and greenhouse gases. Wildfire smoke increases in certain regions. Industrial pollution shifts geographically as economies develop and regulations evolve. Dust patterns respond to drought and land use changes. The atmosphere becomes not only warmer, but also differently textured by the particles suspended within it. High above the surface, microscopic aerosols scatter sunlight through the sky, while altering clouds, rainfall, and planetary temperature. Though individually almost invisible together, they reshape how energy moves through the atmosphere itself. Earth's air grows increasingly influenced not only by gases and heat, but also by drifting particles carried across the world on moving currents of wind. Water vapor moves constantly through the atmosphere in an endless cycle of evaporation, condensation, and precipitation. Invisible moisture rises from oceans, rivers, forests, soil, and ice, before gathering into clouds suspended across the sky. Clouds shape how Earth absorbs and releases energy. They reflect sunlight back into space while also trapping infrared heat beneath them. Through these dual effects, clouds influence nearly every part of the climate system. Clouds form when moist air cools enough for water vapor to condense around tiny airborne particles. Aerosols provide the microscopic surfaces upon which droplets or ice crystals begin to develop. As air rises, pressure decreases and expansion causes cooling. If sufficient moisture exists, condensation follows and clouds appear. Different atmospheric conditions produce different cloud types, from thin cirrus clouds, high in the atmosphere, to towering thunder clouds rising through much of the troposphere. High clouds, composed mainly of ice crystals, often allow sunlight to pass through, while trapping outgoing infrared radiation effectively. These clouds tend to warm the atmosphere overall. Low-thick clouds usually reflect large amounts of incoming sunlight back into space, and therefore cool the surface beneath them. The balance between these warming and cooling effects depends on cloud altitude, thickness, droplet size, and geographic location. Clouds also regulate the distribution of heat and water across Earth. Tropical convection lifts enormous quantities of moisture upward, releasing latent heat into the atmosphere as condensation occurs. This energy helps drive large-scale atmospheric circulation. Storm systems transport clouds and rainfall across continents. Snowfall stores fresh water seasonally in mountains and polar regions before melting later into rivers and oceans. As greenhouse gases warm the atmosphere, cloud behavior changes in complex ways. A warmer atmosphere can hold more water vapor, increasing the total amount of moisture available for cloud formation and precipitation. Satellite observations and atmospheric measurements indicate that global water vapor concentrations have increased during recent decades in response to rising temperatures. This increase strengthens the greenhouse effect further, because water vapor itself absorbs infrared radiation efficiently. Scientists regard this as one of the most important climate feedbacks. Carbon dioxide and methane initiate warming, while additional water vapor amplifies it. At the same time, cloud responses introduce some of the largest uncertainties in climate projections. Clouds react differently depending on region, altitude, temperature, circulation, and aerosol concentration. Certain cloud changes may increase warming, while others partially offset it. Researchers use satellites, aircraft, computer models, and ground observations to study these processes in detail. Observations already reveal measurable shifts in cloud patterns. Some subtropical regions show reductions in low cloud cover, potentially allowing more sunlight to warm the surface. In polar areas, changing sea ice conditions alter cloud formation and atmospheric moisture. Tropical cloud systems respond to warming oceans and changing circulation patterns. Although uncertainties remain regarding exact magnitudes, many studies indicate that overall cloud feedback likely enhances warming rather than reducing it. The atmosphere also experiences increasing extremes in moisture distribution. Some regions become wetter while others dry further. Warmer air intensifies evaporation from soil and vegetation during drought conditions. Meanwhile, storms drawing upon moist warm air can release enormous rainfall within short periods. The atmosphere increasingly shifts water between places and seasons with greater intensity. Atmospheric rivers demonstrate this process clearly. These long, narrow corridors of concentrated water vapor transport immense amounts of moisture through the atmosphere, often above oceans. When atmospheric rivers encounter mountains or cooler air masses, rapid condensation produces intense rainfall or snowfall. Certain regions rely on these systems for fresh water supply, yet stronger atmospheric rivers also increase flood risk. Clouds influence Earth's temperature not only during the day but also at night. Thick cloud cover limits cooling after sunset by trapping infrared radiation near the surface. Clear, dry nights allow heat to escape more efficiently into space. As atmospheric moisture increases, nighttime temperatures in many regions rise faster than daytime temperatures. Observations from weather stations worldwide show a long-term reduction in extremely cold nights. Thunderstorms also respond to changing atmospheric conditions. Warm, moist air rising rapidly into colder upper regions creates instability, capable of producing powerful storms. Increased atmospheric moisture can strengthen rainfall intensity within thunderstorms. Some regions experience greater frequency of severe downpours, though changes in storm occurrence vary considerably by location. Cloud microphysics. The study of tiny droplets and ice crystals within clouds reveals how sensitive atmospheric processes can be. Small changes in temperature or aerosol concentration influence droplet formation, cloud brightness, and precipitation efficiency. Pollution particles may create clouds containing many small droplets that reflect more sunlight yet delay rainfall. Ice crystal formation at high altitude influences cirrus cloud behavior and atmospheric radiation balance. Satellites orbiting Earth now monitor global cloud cover continuously. Instruments measure cloud altitude thickness, temperature, droplet size, and movement. These observations reveal enormous dynamic systems moving across the atmosphere every day. Tropical thunderstorms rise over warm oceans. Polar cloud layers spread across ice-covered seas. Spiral storm systems carry moisture around low-pressure centers. Despite decades of research, clouds remain among the most intricate features of Earth's atmosphere. Their behavior emerges from interactions between radiation, moisture, aerosols, circulation, temperature, and surface conditions across many scales simultaneously. Yet the broad direction of change becomes increasingly clear. The atmosphere contains more moisture, stronger evaporation, and altered cloud patterns compared with earlier decades. Above-Earth clouds drift continuously through changing skies. Thin ice clouds glow faintly in sunlight high above the troposphere. Vast storm systems spiral across oceans. Moist tropical air rises into towering cloud columns visible from space. Rain falls from thick grey layers over forests, plains, and cities alike. The atmosphere now carries greater amounts of water vapor than it once did during the early industrial era. This additional moisture alters the movement of heat through the climate system, while intensifying portions of the global water cycle. Scientific observations reveal an atmosphere becoming not only warmer, but also increasingly humid and energetic. Clouds remain both protectors and amplifiers within this changing system. They shield parts of the surface from sunlight while trapping heat below. They deliver fresh water necessary for life while also driving floods and storms. Across the atmosphere, moisture and clouds continue adjusting to a planet whose energy balance no longer remains stable. Water vapor moves constantly through the atmosphere in an endless cycle of evaporation, condensation, and precipitation. Invisible moisture rises from oceans, rivers, forests, soil, and ice before gathering into clouds suspended across the sky. Clouds shape how Earth absorbs and releases energy. They reflect sunlight back into space while also trapping infrared heat beneath them. Through these dual effects, clouds influence nearly every part of the climate system. Clouds form when moist air cools enough for water vapor to condense around tiny airborne particles. Aerosols provide the microscopic surfaces upon which droplets or ice crystals begin to develop. As air rises, pressure decreases and expansion causes cooling. If sufficient moisture exists, condensation follows and clouds appear. Different atmospheric conditions produce different cloud types, from thin cirrus clouds high in the atmosphere to towering thunderclouds rising through much of the troposphere. High clouds, composed mainly of ice crystals, often allow sunlight to pass through while trapping outgoing infrared radiation effectively. These clouds tend to warm the atmosphere overall. Low-thick clouds usually reflect large amounts of incoming sunlight back into space, and therefore cool the surface beneath them. The balance between these warming and cooling effects depends on cloud altitude, thickness, droplet size, and geographic location. Clouds also regulate the distribution of heat and water across Earth. Tropical convection lifts enormous quantities of moisture upward, releasing latent heat into the atmosphere as condensation occurs. This energy helps drive large-scale atmospheric circulation. Storm systems transport clouds and rainfall across continents. Snowfall stores fresh water seasonally in mountains and polar regions, before melting later into rivers and oceans. As greenhouse gases warm, the atmosphere cloud behavior changes in complex ways. A warmer atmosphere can hold more water vapor, increasing the total amount of moisture available for cloud formation and precipitation. Satellite observations and atmospheric measurements indicate that global water vapor concentrations have increased during recent decades in response to rising temperatures. This increase strengthens the greenhouse effect further because water vapor itself absorbs infrared radiation efficiently. Scientists regard this as one of the most important climate feedbacks. Carbon dioxide and methane initiate warming, while additional water vapor amplifies it. At the same time, cloud responses introduce some of the largest uncertainties in climate projections. Clouds react differently depending on region, altitude, temperature circulation, and aerosol concentration. Certain cloud changes may increase warming while others partially offset it. Researchers use satellites, aircraft computer models, and ground observations to study these processes in detail. Observations already reveal measurable shifts in cloud patterns. Some subtropical regions show reductions in low cloud cover, potentially allowing more sunlight to warm the surface. In polar areas, changing sea ice conditions alter cloud formation and atmospheric moisture. Tropical cloud systems respond to warming oceans and changing circulation patterns. Although uncertainties remain regarding exact magnitudes, many studies indicate that overall cloud feedback likely enhances warming rather than reducing it. The atmosphere also experiences increasing extremes in moisture distribution. Some regions become wetter while others dry further. Warmer air intensifies evaporation from soil and vegetation during drought conditions. Meanwhile, storms drawing upon moist warm air can release enormous rainfall within short periods. The atmosphere increasingly shifts water between places and seasons with greater intensity. Atmospheric rivers demonstrate this process clearly. These long, narrow corridors of concentrated water vapor transport immense amounts of moisture through the atmosphere, often above oceans. When atmospheric rivers encounter mountains or cooler air masses, rapid condensation produces intense rainfall or snowfall. Certain regions rely on these systems for freshwater supply, yet stronger atmospheric rivers also increase flood risk. Clouds influence Earth's temperature not only during the day but also at night. Thick cloud cover limits cooling after sunset by trapping infrared radiation near the surface. Clear, dry nights allow heat to escape more efficiently into space. As atmospheric moisture increases, nighttime temperatures in many regions rise faster than daytime temperatures. Observations from weather stations worldwide show a long-term reduction in extremely cold nights. Thunderstorms also respond to changing atmospheric conditions. Warm, moist air rising rapidly into colder upper regions creates instability capable of producing powerful storms. Increased atmospheric moisture can strengthen rainfall intensity within thunderstorms. Some regions experience greater frequency of severe downpours, though changes in storm occurrence vary considerably by location. Cloud microphysics, the study of tiny droplets and ice crystals within clouds, reveals how sensitive atmospheric processes can be. Small changes in temperature or aerosol concentration influence droplet formation, cloud brightness, and precipitation efficiency. Pollution particles may create clouds containing many small droplets that reflect more sunlight yet delay rainfall. Ice crystal formation at high altitude influences cirrus cloud behavior and atmospheric radiation balance. Satellites orbiting Earth now monitor global cloud cover continuously. Instruments measure cloud altitude thickness, temperature, droplet size, and movement. These observations reveal enormous dynamic systems moving across the atmosphere every day. Tropical thunderstorms rise over warm oceans. Polar cloud layers spread across ice-covered seas. Spiral storm systems carry moisture around low-pressure centers. Despite decades of research, clouds remain among the most intricate features of Earth's atmosphere. Their behavior emerges from interactions between radiation, moisture, aerosols, circulation, temperature, and surface conditions across many scales simultaneously. Yet the broad direction of change becomes increasingly clear. The atmosphere contains more moisture, stronger evaporation, and altered cloud patterns compared with the earlier decades. Above-Earth clouds drift continuously through changing skies. Thin ice clouds glow faintly in sunlight high above the troposphere. Vast storm systems spiral across oceans. Moist tropical air rises into towering cloud columns visible from space. Rain falls from thick grey layers over forests, plains, and cities alike. The atmosphere now carries greater amounts of water vapor than it once did during the early industrial era. This additional moisture alters the movement of heat through the climate system, while intensifying portions of the global water cycle. Scientific observations reveal an atmosphere becoming not only warmer, but also increasingly humid and energetic. Clouds remain both protectors and amplifiers within this changing system. They shield parts of the surface from sunlight while trapping heat below. They deliver fresh water necessary for life while also driving floods and storms. Across the atmosphere, moisture and clouds continue adjusting to a planet whose energy balance no longer remains stable. Near Earth's surface, the atmosphere encounters landscapes shaped increasingly by human construction. Cities rise from the ground in dense concentrations of concrete, steel, glass, and asphalt. Roads absorb sunlight during the day and release stored heat slowly after sunset. Buildings alter wind flow between narrow streets and tall structures. Vehicles, industry, heating systems, and electrical networks continuously release heat and pollutants into the surrounding air. Within urban regions, the atmosphere behaves differently than it does above forests, grasslands, or open water. One of the clearest urban atmospheric effects is the urban heat island. Cities often remain significantly warmer than nearby rural areas, especially during nighttime. Dark surfaces such as asphalt absorb large amounts of solar energy. Vegetation becomes sparse compared with natural landscapes, reducing evaporative cooling from soil and plant surfaces. Tall buildings trap heat within street corridors while limiting airflow. Waste heat from vehicles' air conditioning systems, factories, and electrical infrastructure further warms the local atmosphere. As global temperatures rise, urban heat islands intensify the danger of heat waves. During periods of extreme heat, cities may remain dangerously warm through the night because stored energy continues radiating from roads and buildings long after sunset. Human bodies lose opportunities to cool and recover. Electrical demand increases as cooling systems operate continuously. Vulnerable populations face growing health risks during prolonged heat events. The atmosphere within cities also contains high concentrations of pollutants. Combustion from vehicles and industry releases nitrogen oxides, volatile organic compounds, carbon monoxide, soot, and fine particulate matter. Under sunlight, chemical reactions between pollutants produce ground-level ozone, a harmful gas distinct from the protective ozone layer high in the stratosphere. Ground-level ozone irritates lungs, damages vegetation, and contributes to respiratory illness. Air pollution often becomes trapped near the surface under stable atmospheric conditions. Temperature inversions occur when warm air overlays cooler air near the ground, preventing vertical mixing. Pollutants accumulate beneath the inversion layer, sometimes producing thick smog across urban regions. Large valleys surrounded by mountains may experience especially severe pollution episodes because stagnant air limits dispersion. Climate change can worsen some forms of air pollution. Higher temperatures accelerate chemical reactions involved in ozone formation. Heat waves often coincide with stagnant atmospheric conditions that trap pollutants near the surface. Wildfire smoke increasingly spreads into populated regions during dry, hot seasons, adding fine particles to already polluted urban air. At the same time, efforts to improve air quality in many countries have reduced certain pollutants significantly over recent decades. Regulations limiting sulfur emissions, cleaner vehicle technologies, and industrial controls lower concentrations of some harmful aerosols. Yet many rapidly growing urban areas continue facing severe pollution challenges due to expanding populations, transportation, and energy demand. Cities also modify rainfall and local weather. Urban surfaces heat unevenly compared with surrounding countryside, influencing atmospheric convection. Rising warm air above cities may help trigger thunderstorms under suitable conditions. Tall buildings alter wind flow and turbulence. Aerosols from pollution provide additional cloud condensation nuclei that can affect cloud droplet formation and precipitation patterns. Impermeable urban surfaces strongly influence flooding during heavy rainfall. Water that once soaked into soil now flows rapidly across roads, rooftops, and drainage systems. Intense precipitation can overwhelm infrastructure, quickly producing flash floods in densely populated areas. As heavy rainfall events become more severe in many regions, urban flooding risks increase substantially. The atmosphere near cities also carries signals of human activity visible even from space. Satellites detect heat radiating from urban areas during nighttime. Instruments measure pollution plumes drifting downwind from industrial regions. Carbon dioxide concentrations rise above major metropolitan centers due to transportation and energy use. Artificial lighting illuminates cloud layers from below, altering nighttime visibility across wide regions. Urban vegetation influences local atmospheric conditions as well. Trees provide shade and cool the air through evaporation from leaves. Parks and green spaces reduce local temperatures compared with surrounding built environments. Many cities now expand urban forests and reflective surfaces in efforts to reduce heat stress and improve air quality. Such measures can moderate local conditions, though they cannot fully offset broader climate warming. Coastal cities face additional atmospheric challenges as sea levels rise and storms intensify. Storm surges push seawater into low-lying districts during tropical cyclones and severe storms. Warmer oceans increase atmospheric moisture, raising the potential for extreme rainfall during coastal weather events. Millions of people now live in regions exposed simultaneously to heat, flooding, air pollution, and rising seas. The atmosphere above cities remains in constant motion despite dense construction below. Winds carry pollutants across neighborhoods and beyond city boundaries. Heat rises from streets into the lower troposphere. Moisture condenses above skylines during storms. Urban regions become deeply integrated into atmospheric processes once governed mainly by natural landscapes. Scientific observations reveal that urban populations increasingly experience the combined effects of local environmental change and global atmospheric warming. Heat waves amplified by urban surfaces become more dangerous. Air pollution interacts with rising temperatures. Infrastructure designed for earlier climate conditions faces growing stress from heavier rainfall, stronger storms, and prolonged heat. Cities now act as concentrated expressions of humanity's relationship with the atmosphere. Energy use, transportation, construction, and industrial activity reshape local air conditions directly, while also contributing to global greenhouse gas accumulation. The atmosphere moving through streets and above rooftops no longer reflects the same thermal and chemical balance known during the early growth of industrial civilization. At night, warm air lingers above illuminated roads and buildings. Pollution particles drift beneath streetlights. Heat stored in concrete slowly escapes upward into the darkened sky. Storm clouds gather over coastlines and inland plains alike. The atmosphere surrounding human settlements carries both the immediate imprint of urban life and the broader signal of planetary atmospheric change. Across expanding cities around the world, the lower atmosphere grows warmer, more polluted in many regions, and increasingly stressed by intensifying weather extremes. Human civilization now lives within an atmosphere altered not only globally, but also locally by the structures rising across Earth's surface. Beyond cities and industrial regions, the atmosphere meets forests, grasslands, wetlands, deserts, and soils that cover much of Earth's surface. These landscapes breathe continuously through exchanges of gases, moisture, and energy with the air above them. Plants absorb carbon dioxide during photosynthesis and release oxygen in return. Soil organisms break down dead material and return carbon to the atmosphere through respiration. Water evaporates from leaves and ground surfaces into the troposphere. Across the living surface of Earth, the atmosphere remains closely connected to biological activity. Forests play one of the largest roles in this exchange. Trees absorb carbon dioxide and store carbon within wood roots and soil. Tropical rainforests contain especially large carbon reserves because warm, wet conditions support rapid plant growth throughout the year. Boreal forests across northern regions also store immense amounts of carbon, much of it within cold soils and peatlands beneath the trees themselves. As greenhouse gas concentrations rise and global temperatures increase, ecosystems begin responding in complex ways. Some regions experience longer growing seasons due to warmer temperatures and elevated carbon dioxide, potentially increasing plant growth temporarily. Yet heat, stress, drought, wildfires, pests, and changing rainfall patterns increasingly limit these gains in many areas. Drought strongly influences the relationship between land and atmosphere. When soils dry, evaporation decreases because less moisture remains available at the surface. Plants close tiny pores on their leaves to reduce water loss, slowing photosynthesis and reducing carbon uptake. Dry landscapes also heat more rapidly because less solar energy goes into evaporation and more directly warms the air above. This creates feedbacks in which drought intensifies heat, while heat intensifies drought. Wildfires emerge as one of the clearest signs of these changing land-atmosphere interactions. Fire has always existed within many ecosystems as a natural process. Certain forests and grasslands depend on periodic burning for regeneration. Yet hotter temperatures, prolonged drought, and altered precipitation patterns increase the likelihood of large, severe fires in numerous regions. During major wildfires, enormous quantities of smoke rise into the atmosphere. Carbon dioxide, methane, soot, and fine particles spread across continents. Some intense fires generate towering convection columns that inject smoke high into the troposphere and occasionally into the lower stratosphere. These smoke plumes influence sunlight cloud formation and air quality far from the original fires. The carbon released during fires partially reverses years or decades of carbon storage within vegetation. Burned forests may require long periods to recover, especially under continued warming and drying conditions. In some regions, repeated fires prevent forests from fully regenerating, allowing grasslands or shrublands to replace them over time. Wetlands also play an important role in atmospheric chemistry. Waterlogged soils slow decomposition and allow organic material to accumulate. At the same time, oxygen-poor conditions within wetlands promote methane production by microorganisms. Natural wetlands therefore act as major methane sources. Warming temperatures and changing rainfall patterns may alter wetland methane emissions, though regional outcomes remain uncertain, because some wetlands expand while others dry out. Permafrost regions contain vast amounts of frozen organic carbon stored in Arctic soils. As temperatures rise in northern regions, portions of this frozen ground thaw. Microorganisms begin decomposing previously frozen material, releasing carbon dioxide and methane into the atmosphere. Scientists continue studying how rapidly this process may unfold, because the amount of stored carbon is extremely large. Agriculture has also transformed land-atmosphere interactions across much of Earth's surface. Forests and grasslands become cropland and pasture. Irrigation increases evaporation in dry regions. Fertilizers release nitrous oxide from soils. Livestock emit methane during digestion. Tilling exposes soil carbon to decomposition. Together, these processes contribute significantly to greenhouse gas emissions, while also altering local climate conditions. Deforestation influences rainfall and temperature beyond the immediate area of tree removal. Forests recycle large amounts of moisture through transpiration, the release of water vapor from leaves. In tropical regions, this recycled moisture helps sustain regional rainfall patterns. Large-scale forest loss can therefore reduce atmospheric moisture and alter precipitation across wide areas. The Amazon rainforest provides one important example. Moisture evaporating from the Atlantic Ocean falls as rain across the forest, then re-enters the atmosphere repeatedly through vegetation. This cycling helps maintain humid conditions deep within the continent. Deforestation and warming threaten to weaken portions of this system, although scientists continue studying how close certain regions may be to long-term ecological transition. Grasslands and soils also exchange large quantities of carbon with the atmosphere. Healthy soils store organic material built from dead roots and plant matter over long periods. Unsustainable land use erosion and repeated disturbance can reduce this storage and release additional carbon dioxide into the air. Conversely, improved soil management and ecosystem restoration may increase carbon storage in some landscapes. The atmosphere above natural landscapes constantly responds to seasonal biological rhythms. Forests absorb carbon dioxide rapidly during spring and summer growth. Leaves fall and decay during colder seasons, returning carbon to the soil and atmosphere. Fires release smoke during dry months. Wetlands emit methane as temperatures rise. Deserts lift dust into the sky during strong winds. Scientific measurements increasingly show that climate change is altering these natural exchanges. Satellite observations detect shifts in vegetation growth and wildfire activity. Atmospheric monitoring reveals changing seasonal carbon cycles. Drought and heat stress influence ecosystems across continents. The land surface no longer interacts with the atmosphere under the same stable conditions that shaped earlier centuries. Forests continue breathing beneath drifting clouds. Soil organisms continue breaking down fallen leaves and dead roots. Grasslands sway beneath warm winds. Wetlands release bubbles of methane into humid air. Yet the atmosphere surrounding these landscapes grows steadily warmer, while rainfall patterns shift and extreme events intensify. Earth's living surface remains deeply connected to the atmosphere above it. Plants, soils, fires, and microorganisms all participate in regulating atmospheric composition and climate. As temperatures rise and ecosystems respond, these exchanges become increasingly dynamic and uncertain. The atmosphere now reflects not only industrial emissions and warming oceans, but also the changing behavior of forests, wetlands, soils, and the living landscapes spread across the planet. Far beneath the atmosphere of the present world, Earth preserves records of ancient air within ice rock sediment and buried organic material. These natural archives extend far beyond written history or modern scientific observation. Layer by layer, glaciers accumulate snowfall that compresses into ice over thousands of years. Ocean sediments settle slowly onto the seafloor. Tree rings record seasonal growth under changing climate conditions. Cave formations grow from mineral-rich water dripping through stone. Together, these records allow scientists to reconstruct the history of Earth's atmosphere across immense stretches of time. Ice cores provide some of the clearest evidence. In Greenland and Antarctica, snow falling each year traps tiny bubbles of air before gradually compressing into solid ice. These bubbles preserve direct samples of ancient atmospheres. By drilling deep into ice sheets, researchers recover continuous records extending back hundreds of thousands of years. Measurements of carbon dioxide, methane, dust, volcanic ash, and oxygen isotopes reveal how atmospheric composition and temperature change together through glacial cycles. The records show that Earth's climate has never remained perfectly stable. Ice ages advance and retreat over tens of thousands of years in response to subtle changes in Earth's orbit and tilt relative to the Sun. During colder periods, large ice sheets spread across northern continents, while atmospheric carbon dioxide concentrations decline. During warmer interglacial periods, ice retreats and greenhouse gas levels rise naturally. These transitions unfold gradually across long timescales. What stands out in modern records is the speed and magnitude of recent atmospheric change. Carbon dioxide concentrations measured in ancient ice remain within a relatively narrow range for hundreds of thousands of years before rising sharply during the industrial era. The increase occurs far more rapidly than most natural shifts observed within the ice core record. Methane concentrations show similar patterns of abrupt modern growth. Scientists compare these findings with evidence from ocean sediments, fossil pollen cave deposits, and ancient shorelines. Together, multiple independent records confirm that present greenhouse gas levels exceed those of recent geological history. Some evidence suggests carbon dioxide concentrations may now resemble conditions last seen several million years ago, when global temperatures and sea levels remain substantially higher than today. Tree rings provide another detailed climate archive. In temperate and boreal regions, trees form annual growth layers, whose thickness depends partly on temperature, rainfall, and environmental stress. By comparing overlapping patterns from living and ancient wood, researchers reconstruct climate variations extending back thousands of years in some regions. These records reveal droughts, volcanic cooling events, and long-term warming trends. Corals also preserve climate information. As corals grow, they incorporate chemical signals from surrounding seawater into their skeletons. These patterns reveal past ocean temperatures and circulation changes. Sediment cores extracted from lake beds and ocean floors contain pollen, microscopic organisms, and mineral deposits, reflecting ancient environmental conditions. Each archive records part of Earth's climatic history from a different perspective. Volcanic eruptions appear clearly within many climate records. Ash layers settle onto ice sheets and sediments. Sulfur aerosols temporarily cool global temperatures by reflecting sunlight. Major eruptions leave recognizable signatures across multiple archives simultaneously. These natural events help scientists compare short-term climate disturbances with modern greenhouse warming. The geological record also reveals periods of rapid climate change in Earth's distant past. Some ancient warming events involve massive carbon releases from volcanic activity or methane destabilization. These periods often coincide with ocean acidification, ecosystem disruption, and species extinctions. However, even many ancient rapid events generally unfold more slowly than the current industrial increase in greenhouse gases. Sea levels provide another long-term measure of atmospheric and climate conditions. During ice ages, large volumes of water remain locked within continental ice sheets, lowering sea level dramatically. During warmer periods, melting ice raises sea level across the globe. Geological evidence from coral terraces, coastal sediments, and ancient shorelines shows that sea levels respond strongly to sustained warming over long timescales. Modern observations already detect accelerating glacier melt and ice sheet mass loss in Greenland and Antarctica. Mountain glaciers retreat across most regions of the world. Arctic sea ice declines rapidly during summer months. These changes align with atmospheric and ocean warming measured independently through thermometers, satellites, and ocean instruments. The atmosphere itself now contains signals measurable across many scientific fields simultaneously. Ice cores record rising greenhouse gases. Thermometers show warming temperatures. Ocean heat content increases steadily. Species distributions shift toward cooler regions. Growing seasons lengthen in many northern areas. Snowpack declines. Heavy rainfall intensifies. Together, these observations form a consistent picture of a climate system responding to altered atmospheric composition. Uncertainty remains regarding the precise pace of future change. Ice sheet dynamics, cloud feedbacks, ecosystem responses, and regional climate patterns remain subjects of active research. Yet the fundamental direction of atmospheric transformation appears increasingly clear within both modern observations and Earth's deep climate history. Ancient records show that the atmosphere can change profoundly over geological time. Continents move, volcanoes erupt, oceans circulate differently, ice sheets grow and vanish. Life itself alters atmospheric chemistry across billions of years. Yet the current atmospheric shift unfolds during a uniquely observable moment. Satellites circle Earth continuously. Weather stations measure temperature each hour. Atmospheric gases are monitored precisely at remote observatories across the planet. The atmosphere surrounding modern civilization now differs measurably from the atmosphere that shaped earlier human history. Greenhouse gas concentrations rise beyond natural ranges recorded in recent ice core history. Heat accumulates throughout the oceans and lower atmosphere. Weather systems respond with increasing extremes. Upper atmospheric layers cool and contract, while the troposphere deepens below. High above Earth, the atmosphere still glows blue beneath sunlight and darkens gradually into space. Winds continue circling the globe. Clouds gather above oceans and mountains. Snow falls across polar ice sheets where future records slowly form within accumulating layers. The atmosphere remains alive with motion and change as it always has. Yet the evidence preserved in ice, stone, water, forests and air now indicates that Earth has entered an atmospheric state no human civilization has previously experienced. The transformation unfolds not within myth or distant geological abstraction, but within direct observation across the living planet itself. The atmosphere changes slowly enough that daily life often conceals the scale of transformation unfolding across the planet. Clouds still drift above forests and oceans. Rain still falls onto fields and cities. Winds continue crossing mountains, deserts, and polar ice. Yet within these familiar movements, the balance of Earth's atmosphere steadily shifts. Far above the surface, the highest atmospheric layers cool and contract, while solar storms continue sending energy into near-Earth space. The mesosphere grows colder and luminous, noctilucent clouds appear more often near the poles. The stratosphere changes through ozone recovery and greenhouse cooling. Jet streams adjust their pathways across warming regions. Beneath them, the troposphere deepens as heat and moisture accumulate within the lower atmosphere. The oceans absorb immense quantities of excess energy, while releasing increasing moisture back into the sky. Storms gather strength from warmer seas. Wildfire smoke spreads through heated air. Forests, wetlands, grasslands, and frozen soils alter their exchange of gases with the atmosphere above them. Cities trap heat beneath concrete and glass, while pollution and rising temperatures combine near the ground. Across the world, instruments continue measuring these changes with growing precision. Satellites observe shifting clouds, shrinking ice, rising seas, and warming oceans. Ice cores preserve ancient air beside the chemical signature of the modern atmosphere. Weather stations record warmer nights, heavier rainfall, and longer heat waves. Earth's atmosphere remains dynamic, interconnected, and alive with motion from the edge of space to the soil below. Molecules drift, clouds condense, winds circulate, and sunlight moves across oceans and continents as it has for ages beyond memory. Yet the atmosphere now carries a different composition, a different energy balance, and a different future path than the one known by earlier generations.